Hi and welcome everybody to the lecture titled the Quadrature Amplitude Modulation, which is part of a series of lectures related to Introduction to Communication course. We discussed up until now double sideband suppressed carrier modulation, amplitude modulation, which is with unsuppressed carrier, and then we discussed single sideband modulation, and then we talked about last one, vestigial side modulation. And all these are analog modulation schemes. We use them in analog communication systems to transmit our data reliably to our receivers. So each one of these modulation schemes can be used for certain applications. Each one of these modulation schemes has its own advantages and disadvantages, or merits and demerits. So based on the merits, based on the characteristics of the modulation scheme, you need to know to which application you can apply it. Now, we are going now in this lecture to talk about the quadrature amplitude modulation. So this is basically for the ones who are interested in understanding quadrature amplitude modulation, from telecommunication engineers and electronic engineers. And we are going to cover the transmitter design, receiver design, the modulator part and demodulator part mathematically and graphically, and by block diagrams. So basically you need to acquire knowledge in all of these parts and to be able to relate things with each other and understand the whole pictures in a coherent manner. So double sideband single suppressed carrier modulates a signal with bandwidth B to a transmitted signal with bandwidth 2B. Yes, we know this. And single sideband modulation reduces the transmitted bandwidth to B. But what's the problem? The problem with single sideband, that's why we said single sideband is more spectrally efficient than the previous modulation schemes. But the problem, single sideband requires more complex modulators. Yes, very complex processing at the transmitter and at the receiver as well, and reduces signal to noise ratio for a fixed carrier amplitude. So these are the two problems with single sideband. So we like the fact that it's spectrally efficient and utilizes your bandwidth effectively and doesn't waste it too much. But the problem that it's so complex and it reduces the signal to noise ratio, which means sometimes cannot be reliable. And the other third problem that I can add is the fact that it can be applied only to specific parts of the signals of the like audio, but it cannot be applied for video or images, for example. That's why we are going to study QAM, which is a modulation scheme that can improve your spectral efficiency while avoiding complexity and not reducing the signal to noise ratio significantly. But the QAM we are talking about here, analog QAM. So basically, in digital modulation, in digital communication course, we will talk about the digital QAM modulation scheme. So in quadrature amplitude modulation uses the 2B transmitter bandwidth to send two independent signals. So 2B bandwidth to send two signals. This means for each signal we have 1B, which is spectrally efficient kind of. So what's the transmitted signal in this case? The mathematical formula of the modulated signal. You basically take your message signal M of t, multiply it by the first carrier cosine 2 pi of ct, and then you take the second signal that you want to transmit, M2 of t, you multiply it by another carrier which is orthogonal to this. They must be orthogonal to each other. This is must. If you cannot satisfy this, then we cannot call this quadrature amplitude modulation. It has to be orthogonal. So everybody knows from math 1, math 2, calculus that sine and cosine, they are orthogonal to each other. The dot product operation of these two signals is equal to 0. You can verify it and check it again. Yes, everybody agrees on that. A QAM, now since we are using 2B to transmit two signal, this means 1B for each signal, which is kind of similar to the spectral efficiency of single sideband. Yes, has the same spectral efficiency as single sideband. And we know all why spectral efficiency is important. Let me remind you of the importance of spectral efficiency if you forgot it. I need to make sure that you feel and realize the importance of this issue. We said one time in the lectures, we discussed in the previous, like before 1 month, 2 months, at the beginning of the course, we said that bandwidth is a very precious resource. The companies use the bandwidth in order to serve more customers, to make you able to use more application and increase the speed of the internet. Now, from where they got the bandwidth? They get the bandwidth from the government. The government licenses this bandwidth spectrum to the companies. For some money, the company pays for the government, and usually the company pays millions of dollars to the government in order to take certain bandwidth, a portion of the bandwidth, for example 1 mega. But since it's very expensive, the bandwidth is very expensive, we must make the most use out of it. Yes, use it efficiently, wisely. You know, it's kind of using it without any wastage. You must make sure that you can use it as effective as much as you can. And that's why we are always trying as engineers to invent and come up with modulation schemes that are spectrally efficient, that can save us money, save the companies money, and you can make the most use of the spectrum. So single sideband has same spectral efficiency as QAM, but doesn't need sharp band pass filters. This is the good thing about the QAM here. You don't need sharp band pass filters. Yes, and this is very nice thing to have, because most of the complexity coming in single sideband is due to the fact that we are using sharp band pass filters. And what does this mean? This means that we are doubling the spectral efficiency while not increasing the complexity of the system. And this is very important and very crucial and vital in the design of communication systems. Yes, you can come up with a modulation scheme that can improve the performance, but it can be on the other side so expensive in terms of design. It can be so expensive in terms of complexity. So we don't want this. We usually prefer the techniques and methods that can achieve significant gains in the spectral efficiency and other performance metrics, while we are simultaneously making sure the complexity is not that high. If you can achieve this and you propose this to the community, then they will buy it from you and take it from you and license it from you. They like these kind of modulation schemes. So QAM is used in almost all digital communication methods up until these days. Your mobile phone is using a QAM, yes, in order to make sure that it can serve you with the required data rate, with the speed of the internet you like and you want. So it's used in telephone modems, in mobile cellular network, in cable TV, satellite TV, 1G, 2G, 4G, 5G. It's indispensable. Everybody's using it in most of the systems. So such an important modulation schemes, at least you must have an idea about it and how it works and what's the block diagram and how do we modulate the signal and receive it at the receiver. So let's show you the block diagram, the basic block diagram. Two real messages, M1 of T and M2 of T. M1 is modulated on a cosine and M2 is modulated on a sine. And this is basically your transmitter. So here you have the transmitter part, and here you have the receiver part, and here you have the channel, the medium, the propagation environment. This is H, we call it channel. So this is receiver, your mobile phone, and this is tower, let's say, and you are communicating by using a QAM modulation. You multiply the first signal by cosine 2 by fc, the second signal you multiply it by sine 2 by fc, and what happens then? You sum them on top of each other. You sum this signal with this signal on top of each other to get another signal. Now you tell me, okay, we are summing them, putting them on top of each other. How come they don't interfere with each other? They don't cause any interference. I tell you, because we choose the carriers sine and cosine orthogonal to each other. We choose them in such a way that we can detect them at the receiver easily. We can separate the signal. Look what happens at the receiver now. This is the receiver. You send your signal through the from the antenna through the channel until it reaches your receiver. It can travel 3 kilohertz, 3 kilo, like it can travel any distance you want, 3 kilometer, whatever, based on the system that you are designing. But at the end of the day, once it reaches the receiver and it hits the antenna, the electromagnetic signal here generates electrical signal that can go to the RF chain of your receiver, and then once you take the whole signal, this plus this composed with this, you take this whole signal and multiply by cosine. Since the composite signal here, 1 and 2, they have one cosine and the other one is sine, when you multiply by cosine, you just take the part of the signal that's parallel to the cosine and you ignore any signal that's not in the direction of cosine. What's that signal that's not in the direction of cosine? It's sine. When cosine gets multiplied by sine, the result is 0. So basically, you totally ignore and remove the signal related to M2 here when you multiply by cosine. And you get your signal, you use low pass filter, and then you get M1 of t. What happens on the other part? You take your composite signal. Composite signal is the summation of this signal and this signal. You multiply it by sine. Once you multiply it by sine, you take only the part aligned or in the parallel direction of sine. While the other part of the signal, which is in the direction of cosine, since cosine is orthogonal and perpendicular to sine, when you multiply them using dot product operation, you get 0. So this means that you only get M2. And now you have M1 of t, M2 of t, and your message is received successfully. So this is the amazing thing about this modulation scheme. Now, I hope one of you in the future, he can continue studying modulation schemes and communication, and he becomes the expert in it. And he thinks, cannot we use another orthogonal carrier here and send? If we can use, then we can treble the spectral efficiency. If we can use another one also here, cannot we use another one? Now, up until the time, as the time I'm talking right now, there is no such solution. I mean, orthogonal signal while using the same time, same frequency. Yes? And they are orthogonal to each other. They don't cause interference to each other. If you can come up with another carrier beside cosine and sine, which can be orthogonal to sine and cosine, then you will be the second genius in communication system. Yes, you understand me, the importance of this, the research area. If you want to work in the future on this problem and become the genius and very well-known guy or researcher in the world, bring another signal that's orthogonal to sine and cosine and send another M3, so that you treble, you make the spectral efficiency 3 times. And if you can bring another signal that's orthogonal to the previous 3 and get quadruple spectral efficiency, then you are the second genius. So this is an amazing problem. I don't know any solution to it in the literature. increasing the spectral efficiency by finding new carrier signals that are orthogonal to sine and cosine. To solve this problem, most probably you need to be expert in math, because it's all about math. If you can prove that there are other signals that are orthogonal to sine and cosine besides sine and cosine, then you can solve the problem. So the solution comes first from math, and then you apply it to communication. Now, we achieved doubling the spectral efficiency, we achieved improving the spectral efficiency in this case, but what's the price? At which cost we are achieving spectral efficiency? At the cost of the need to have synchronous receiver. What do I mean by synchronous receiver? I believe this is the first time to hear it, or did we talk about it before? Synchronous receiver means that the transmitter and receiver carriers, they must have exactly the same phase shift. No mismatch between them, because any mismatch will cause some degradation in the performance of your system. Or the two channels will interfere with each other and cause some performance degradation. With a 90 phase shift, if you put 90 phase shift, the signals will cancel each other totally. You will not be able to receive your message signal at all. So you must be careful. You must make sure that those carriers, they have the same phase shift. And one of the ways to make sure that this is doable, and we guarantee this, is to use phased lock loop, where it makes sure this circuit is responsible for making sure the phase at the transmitter is the same as the phase of the carrier at the receiver, and you don't get any problems. Now, if the input spectrum looks like this question can be in the exam. Yes, if the input, yes, this signal, this is, call it M1 of F, and this is the first message, and this signal is M2 of F, and this is the second message. And I tell you, modulate this using QAM. Show me the graphical representation of the modulated signal in the frequency domain. This is the question. You tell me, when I multiply this by cosine, I get two copies of the signal, one in the negative, one in the positive. So these are the two copies. Agrees with me? These are the two copies, one here and one on the other part. What about the other signal, M2 of F? Since I'm using a QAM modulation, I need to multiply it by an orthogonal carrier to the cosine. What's the orthogonal carrier to the cosine? Sine. When you multiply by sine, you also get two copies of the signal. But note, sine, the phase spectrum of sine has negative, minus. So the spectrum component in the negative side is positive, and the spectrum component in the positive side is negative. So basically you get these two signals. So this is your signal. This is your signal in the frequency domain. Can you see with me? Can you see and notice with me that the two signals are using the same frequency? Yes? And if you draw them in time, they also use the same time. They are on top of each other. So as you can see, they are orthogonal on top of each other, means superimposed to each other in time and the frequency. But you can separate them nicely. Why? Because they are orthogonal. Mathematically, they are orthogonal. When you make the dot product operation, they get separated. Now, what do you do at the receiver? You receive this signal. What do? You multiply. You take this signal and multiply it by cosine to get this part, the blue part, and you multiply the same signal again by sine to get what? To get the red part, this purple part. Is that clear? This is QAM modulation. This is the most effective modulation in terms of spectral efficiency up until now. So up until now, we have discussed many different ways to encode information as amplitude in the analog modulation. One, amplitude modulation. Second, double sideband, single carrier, suppressed carrier AM, single sideband modulation, vestigial side modulation, QAM modulation. For each one of these, let me remind you, you need to be able to draw the signal in frequency domain before the modulation, after modulation, and before demodulation and after demodulation, and write the mathematical equations before and after modulation and demodulation, and draw them. The same here. You draw it in time, in frequency, you know the block diagram, you know the mathematical equation at different points of the transmission series, transmission block diagram or receiver block diagram. And the same here, the same here. What else you need to know? You need to know the motivation behind each one of this. What are the advantages and disadvantages of each one of these? And why do we need to use QAM? What's the unique thing about the QAM compared to single sideband? Why do we need to use vestigial sideband? For which application vestigial sideband? You need to know these things. Once you know these things and you are comfortable with them, and you can know these things only if you were attending the lectures regularly. You don't need to study for the exam even if you were attending the lectures and taking notes. But if you didn't attend or miss some of the lecture, you have to go back now to the YouTube and watch all the other previous lectures that we gave and presented to modulation schemes one by one, and make sure you understand the ins and outs of each one of these modulation schemes in terms of drawing, mathematical derivation, mathematical operation, and graphical representation and the block diagram processing at the transmitter and receiver, and know the advantages and disadvantages of each one of these. The common issues that we noticed for all these modulation schemes is synchronization, basically. First, synchronization, and the second, the bandwidth. We try to make the bandwidth more spectrally efficient. And this is it for this class, and thank you very much for your attention, and we continue in the next part hopefully very soon. Thank you.